Play mode.
Hello everyone, I'm Mike Gesvick with the National Renewable Energy Laboratory, and welcome to today's webinar hosted by the Building America program. We're very fortunate to have Tom Scherber, Steve Scherber, Anastasia Herc, and Duncan Kroll joining us. This group will focus on specific Building America projects and case studies that highlight real-world examples of deep energy retrofits achieving both technical and market success. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or over your telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side of the display, the box on the right side will display the telephone number and audio pin you should use to dial in. Panelists, we ask that you please mute your audio device while you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826. If you would like to ask a question, we ask that you use the questions pane where you may type in your question. If you are having difficulty viewing the materials through the webinar portal, you will find PDF copies of the presentations at the website listed here, and you may follow along as our speakers present. Also, a recording of the webinar will be available on the DOE YouTube channel within a few weeks. Here is the agenda for today's webinar. Before our speakers begin their presentations, I will provide a short informative overview of the Building America program. Following the presentations, we will have time for questions and answers. Building America is a public-private partnership focused on advancing the whole house performance of residential buildings. There are 10 industry consortia teams and a number of national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and contractors, to conduct a wide range of research and development projects for the residential building industry. These organizations often have regional specialties, but are also national in scope, with the ability to reach key decision makers in a variety of related industries. The Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for nearly 20 years. We also have created useful and free tools for the industry to gain access to all of the knowledge that this program has to offer, including the Building Energy Optimization Program and the Building America Solution Center. We focus on researching how the components of new and existing homes work together through systems integration. Energy performance, durability, quality, and affordability have always been at the top of our priority list. As our research progresses, we are tackling new problems and investigating new ways to add value and drive changes in the performance across the residential industry. In the nearly 20 years that Building America has been doing systems integration research, we've spearheaded many ways to combine ultra-high efficiency with high performance in both new and existing homes. These attributes are often not mutually exclusive. High performance, when more broadly defined, often results in high efficiency. Recently, the Top Innovations Recognition Award was established for the program. Refer to the Building America website for a complete list of innovations that have changed home building in North America. To explore many of Building America's practical solutions to building a better home, refer to the Building America Solution Center to learn how to specify, install, and verify the latest in home building technologies. The topic today is high-performance enclosure strategies, Part 1, existing homes. The goal with this webinar is to share ongoing research being completed by Building America teams. If you would like more detailed information about any of these efforts, or if you're interested in collaborating, please feel free to contact any of our presenters. I'll provide a brief introduction for our distinguished panelists. Our first speaker today is Tom Scherber. Tom is a fellow at the University of Minnesota and has extensive experience working across a range of housing types and currently focuses on affordable housing technologies for cold climate applications. Next up is Steve Scherver. Steve is the General Manager and Principal at Cocoon Insulation, where he applies his over 20 years of practical field experience to solving challenges associated with insulating new and existing homes, installing radon mitigation technologies, and other diagnostic services. We will also hear from Anastasia Herc, who is a Building Performance Specialist from Ivicus. Anastasia is an architect by training and works with the Ivicus Building Performance team. We'll also have Duncan Prawl from Ivicus on the line during the Q&A session. Duncan is a Senior Research Architect at Ivicus. With that, I would like to welcome Tom to start the presentation.
Good afternoon, everybody. Thanks for the introduction, Mike. I trust that you can all hear me. And I also want to thank Heather and Mike from NREL and from Confluence for putting this thing on. It's kind of a good opportunity to share some of the research that we're doing in the field. Today I'm going to talk about retrofitting insulation on foundations. And yes, excavationless is a word, and we'll hear more about that a little bit later. With the Northern Star Building America team, as Mike said, and on this project I also have co-workers Garrett Moseman, who is a Senior Research Fellow for the University of Minnesota at the Center for Sustainable Building Research, and Cindy Ochek is a talented green designer, contractor trainer, and writer, and does a lot of work for us. Our industry partners are Cocoon, BASF, a chemical company that designed a specific liquid foam for this process, American Environmental, hydrovac excavation contractor, and Urban Homeworks, a nonprofit affordable housing developer. So there are two ways you can retrofit insulation on foundations. One is interior and one is exterior. They both have benefits and downfalls in how they will perform, and I think it's a matter of looking at all the needs for a particular house in order to decide which is best. But we've come up with a way to work on the interior or the exterior side, and that's what we'll be talking about today. Interior insulation can work. There's a lot of issues potentially with moisture control, and sometimes it's not a very continuous on the inside because you're not accessible to the entire exterior wall. Exterior insulation can be problematic because it costs a lot of money and wrecks the landscaping as they dig around a house and things like that. So we've come to look at this issue and how can we better serve organizations and builders and homeowners that want to insulate their house, but for some reason or another can't do it from the inside. The house you see here is our subject house. This is one of 2 million houses a year you see across the country in urban areas in a category called boarded and vacant homes. A lot of times these homes are turned over to the city or county because of foreclosure or other economic conditions. And then nonprofits such as Urban Homeworks, Habitat for Humanity, and others will pick up these houses and bring them back to life and put low-income families in them and provide other services, socioeconomic based. And we work a lot with Urban Homeworks because they want to continue to improve their ability in remodeling homes that perform better. And the reason they want to do that is because their mission goal is to promote and serve the well-being of vulnerable families, and to put them in a house that doesn't do the exact same thing would be counterproductive to them. So before we get started, I just want to throw out a question in reference to insulating, retrofit insulating foundations. If there was a way that I could surgically remove 3 inches of soil from the exterior all the way around the foundation, 8 feet deep, just 3 inches, and then fill that trench up with a liquid foam and walk away and call it insulated, would you want to know about that? Well, I think we found a way to do that. This little toy here is called a vacuum excavator. It is a type of tool that's actually been around for 30 years. They work in the utility industry primarily. You see these kind of vehicles with in the streets with their the tube going down into manholes where they clean out utility chases. They also dig potholes looking for buried vulnerable wires and pipes that you might not be able to dig with a mechanical digging machine. But this machine is able to evacuate through suction large amounts of soil and debris very quickly. It has a 10-yard tank on the back, and it can generate vacuum pressure at a rate of 5,500 cubic feet of air per minute. And it'll draw, it'll pull debris through the tube at about 220 miles per hour. This is a small one. There are larger trucks that do this kind of work. So we got together with some contractors and interviewed them and decided to go ahead with this project. Now what I'm about to show you is a little bit raw for 2 reasons. One, because I took most of the pictures, and 2, because we got a team of experts together, contractors and consultants and whatnot, and we had sort of a plan on paper, but we actually showed up on site on a nice sunny morning and decided we'd figure this thing out. Now the truck can vacuum this debris through up to 400 feet of hose. So it actually can park in the street and wrap that hose all the way around the house. Doesn't even have to come onto the site. Basically, I'm going to show you a series of photos that shows the methodology that we use. They take high pressure water, 3,000 psi. You can see the little water pressure washer to the right there, just off the shelf Home Depot pressure washer, and that is used to cut the soil at a precise 3 to 4 inches, and then the big hose will vacuum out the debris. Now the truck has a very large compressor and a high pressure water system, but it runs at about 10 to 12 gallons per minute, whereas this little one runs at 2.7 gallons per minute, and we wanted to take out or actually put as little water into the trench as possible. So what they do is they start digging in the middle of a wall and sink that 8-foot pipe that's 8 inches diameter all the way to the bottom. And it just stays in the center. You can kind of see the larger hole right here. And then the pressure wand will push the loosened soil and mud slurry over to the vacuum hose, and it'll vacuum it up and then create a trench all the way around the house. Now you notice this is a 1906 house with an old rough stone-faced foundation, and that's one of the reasons why we use the liquid foam. Again, just another shot of the trench going down, in this case about 6 feet. Another shot of the wand cutting the soil and pushing it over towards the vacuum tube. It's sucking it out into the truck as we speak. This is an example of what we ran into with this house. The thing we don't know when we go to dig without a core sample is what the soil is like next to the foundation. One of the good things about this project is we ran into every worst case scenario possible, I think. There were rocks and pipes and stones and metal objects down there that got in our way, and we had to dig them out. But what we learned is it didn't slow us down that much. With a couple people picking out rocks and so on, and the water pressure hose pushes dirt and mud around anything that's there, so you can clean it out rather easily. Here's just a shot from a distance, and as you can see, there are 3 supervisors for every 2 workers, as normal. Again, another shot of the hose in the middle of the wall, and then you go from each corner and push the dirt towards the hose. Another shot of excavation or digging with the water. Now here's an example of what we call a cave-in. This is soft soil. This is where a window well was, and when we got close to it, it caved in. And we weren't prepared for, or we didn't know that whether or not this would happen, but we talked about what we would do. And without skipping a beat, the excavator, this is where it really shines. When it has loose soil, it can move that entire pile out into the truck within 3 to 4 minutes. It was just amazing. And then the digger just kept right on going. And I'll show you what we did to backfill in that area so that we, when we poured the foam in a few minutes. So the foam was designed by BASF, a large chemical company, and they designed it specifically for this application, so it would go into a cold, wet condition and stay there, and it would resist degradation below grade while it encountered moisture all the time. And all we did is we took, that's a regular spray system, but it's with a different nozzle that actually drizzles it out in a liquid form. And the 2-part polyurethane foam would just be poured in back and forth, and slowly rise upward. And it strongly adhered to everything in its path, including the stone foundation. So we went around the building, slowly filling up the trench and bringing it up to about 6 inches below grade. We stopped there, and we did that because we wanted to begin a transition piece up to the top of the rim joist, which is located about up here, I think. And to make that look good, we wanted to use a smooth, rigid foam so that we could put a parging coat on there and finish it off. So all the way around the house, we stopped at 6 inches below grade. Now here's an example, just to backtrack, of another cave-in. This was a room that was torn off, and so this was uncompacted soil. And when we started digging, it caved in. And Bill here, who's an experienced field guy, he just grabbed a piece of plywood, slapped some poly on there, leaned against it, filled it up with foam, and hardened within a few minutes. And then, of course, foam doesn't stick to the poly, and he pulled it right out and moved it down and kept right on going. Quite a handy guy. So then the above grade transition, we put small furring strips, 1.5 inches, 2x2s, and nailed 1.5 inches rigid foam on, and then we did that all the way around the house. If you look down on the bottom left here, we fused the bottom edge of the rigid foam to the liquid foam, so there was a continuous insulation from the bottom of the trench all the way to the top of the rim. Once we got this foam at the level above the rim joist where we wanted it, we experimented with how the foam would rise behind there. We were concerned about the expansion and whether or not the rigid 1.5 inch foam would hold the foam in place and not bow out. We were told it was a low expansive foam, so we were confident, but we weren't sure. So the foam starts coming up, and right away you can see it starts bowing out right there. So what did we do? We stood around, scratched our head. How do we build some kind of form to attach here so we can keep that wall straight? In the meantime, Bill grabs another slab of plywood and some screws, and he just screws it right into the rim joist and doesn't even quit. He just keeps it right on going, fills the back end with foam. And we were able to get around and without losing any time. So all the way around the house, then we have 3 inches above grade foam, and on that smooth surface will be a concrete or a stucco parge that will be then capped. Here's an example of a different project where they capped the top with a metal flashing edge over the parged foam, and then they bumped out a trim piece in the rain cap right below the siding. So architecturally looks kind of nice. This house, they were going to continue with insulation up from the below grade or the foundation insulation. They're using a nifty product called InsoFast right here. It's an EPS 2.5-inch thick product that's got built-in furring strips that are approved for hardy siding. So when you mount that on the wall, you're able to hang your siding and you've got exterior insulation. So what we did is we just put peel and stick membrane over the top of the edge. We put a little wedge here all the way around to create drainage underneath the foam. And then this is building paper that goes over the top. Kind of a standard situation. Works kind of nice. So in order to achieve the goals of the Building America program, which is to reduce energy consumption 30 to 50% and even more, we have to include insulation of foundations. And there are, according to the census, there are about 88 million single-family homes, another 40 million rental units, all with various types of foundations, some with partial foundations, some with crawl spaces, some with slab on grade. But this method will work on homes with finished basements, homes with inaccessible basements that otherwise wouldn't have their basements insulated because they didn't want to go outside. Their landscaping was too expensive. Works on homes with crawl spaces or homes, rental homes in townhouses, apartments, and buildings that have slab foundations. Home and buildings needing waterproofing and drain tile, building that needs foundation repair. And we can also insulate under porches and sidewalks because we can tunnel underneath those items and fill it full of foam without skipping a beat. Also, I've seen videos of, we haven't done this, but they can dig, you can go into a basement and where people want to put interior drain tile, they end up chopping the floor all the way around the perimeter. Well, one excavator was able to dig a 10 by 10 hole, cut a hole in the cement, 12 feet away, cut another 10-inch by 10-inch hole, and then 12 feet, every 12 feet all the way around, and then they would tunnel with the excavator vacuum tube and suck out all the dirt underneath between the two holes, fill it with gravel and slide the hose in there, and then have only 10 by 10 squares of concrete to patch in. I also saw them doing underpinning under foundations by digging out with the excavator, so there's quite a bit of opportunity to use this methodology in retrofitting homes. The cost real quickly, the top line up here is an actual home that was done with a conventional power shovel or backhoe. The labor for the backhoe is $2,900. The house is very similar to our house, which is 36 by 28. So we tried to use a close comparison. Labor cost was $2,800, and then the foam was $9,600, 3-inch XPS they used there, and a peel and stick water barrier, $7,600. The home that I just showed you, that cost would have been, a lot of that stuff was donated, about $6,500, but we had an average of 4 inches width at a board foot rate of $1.50 per board foot. So we ended up spending more money on foam than we really would have wanted to. And then the rigid foam above grade was $698. The hydrovac cost for $1,600 for $6,500. But that's not the bad news yet, because when we were estimating the cost for a second project, we had to come up with a way, Steve at Cocoon and I, to be more accurate in how much it would cost to do the foam. And what we decided to do was just continue the rigid foam form that you see on the above grade portion all the way down to the bottom. In other words, use approximately an 8-foot sheet. And instead of using wooden furring standoffs, we would cut 1.5-inch, 4 by 4 inch little footies and glue them to the back side, drop it down in the hole, push it against the foundation, backfill it with some dirt, and then all we had to do was fill the entire 8-foot depth with 1.5-inch foam. Very easy to estimate how much that would cost. And it actually brought the cost down because of the cost of rigid foam versus liquid foam to $3,792. This is the next house that we're going to do with Urban Homeworks. This is actually going to be a full overcoat from the foundation all the way up the sidewalls, and a full roof overcoat, which you'll learn more about in the upcoming presentations. One thing I forgot to mention, you can trench and insulate all winter long through frozen soil. This is one of the first winter-friendly retrofits that actually probably works better in the winter because you're not going to have cave-ins. You're going to be able to precisely cut. All these trucks have, or most of them anyway, have 450,000 BTU water heaters for doing this very thing, cutting through 3 feet of ice, which is kind of a nifty thing. And then finally, here's a project we're also going to do this summer. This architect is renovating this house, has 9-foot ceilings in the basement with a very artistic stucco or plaster finish on the walls, and she can't insulate on the inside. So we're going to go around this house and insulate it for her, and she wants to be part of the research. So that is my last slide, and I'm going to turn this back to the moderator.
Thank you. I think we'll just transition next to Steve.
Steve, you might be on mute.
Steve, you there?
I am. I'm sorry. I was just trying to make my screen viewable here. Okay. Is that viewable?
Yep.
Okay. Thank you for having me here. My name is Steve Scherber. I'm with Cocoon. We are an insulation contractor here in Minneapolis, Minnesota. And what I'm going to talk about here is a specific project here called Project Overcoat. And Project Overcoat, it was specifically targeting particular house type, the house type of a story and a half. And the purpose of this project really was to try to come up with a solution for the story and a half situation with houses with severe ice dams. Typically a story and a half has an already finished upper area, and so retrofitting from the inside is typically complicated or not possible, at least not cost effective. And so moving to an exterior approach was the option that we went to see if we could see how feasible it was. We looked at a lot of the current story and a half methods that existed out there, and we've tried a lot of them as well. So we used that as sort of a baseline to see how much better this overcoat project would perform. And then what I'm going to go through here is actually 2 case studies, 2 houses that we did to show you in detail what the construction process looks like. And then I'll go over what some of our findings were on each of those projects. So the purpose here was solution to ice dams and other related problems associated with the story and a half. We wanted to test the exterior thermal moisture management system termed EDMS as a roof-only approach for maximizing opportunities for insulation, air sealing, and roof deck ventilation. And then we wanted to compare the EDMS approach to the current methods out there. So in general, a story and a half, just for those of you that haven't seen or aren't familiar with exactly what a story and a half is, these would be some examples of story and a halves where the first story is full 8-foot walls, the second story really exists underneath the roof, and so you end up with portions of the upper area that look like they have slanted sidewalls or ceilings, smaller flat attics, and then these side attics that flank the front and back of the house. Okay, why the story and a half? Mainly this represents a common building type. It's a really prevalent house, and there's a lot of opportunity out there to fix it. This house typically has performance issues. They're very difficult to retrofit without going to the outside. So some of the problems that we see with story and a half are durability issues, ice dams, comfort, air quality, moisture issues, and utility costs. So the main reason we identified that story and a halves are a problem, more so than other houses, are primarily these boundary conditions. It's very complicated to maintain the boundary conditions, and by that I mean air, vapor, thermal, and moisture control when you've got a lot of really complex surface areas and you're trying to retrofit that in the upper area of the story and a half. These story and a halves are problems primarily because these are attics that were not originally intended to be finished, but because it's really cheap real estate and square footage here in the house, it's low-hanging fruit as the next thing to finish. We have a desire when we finish these attics to maximize space, so we don't typically, when we finish a story and a half, we don't typically fur down the walls and the ceilings to the appropriate depth so that they can be fitted with proper venting paths and proper R-value depths with insulation. We're typically using a roof for a wall, and that's typically occurring on the slant portion where you've got a 2x4 roof rafter that is now containing roughly 3.5 inches of insulation at best for a good portion of that upper area. And then we create these confused spaces, and this is a term that I like that sort of describes the side attics. And the side attics are confused because they really don't know if they're inside or if they're outside. And so if it's inside, it needs to be conditioned to the same temperature as the rest of the air on the inside. And if it's outside, it needs to be vented and communicating with the outside air. And a lot of times we're not able to get venting into those spaces, so we create this confused space. And as well, we're not running supply ducts and returns into those spaces so that we're conditioning them the same way we would in the living space. And of course, doing these projects, the devil is in the details. In theory, we can say, yeah, we want to insulate the outside of the house, but really it comes down to the details of how we do that. So our performance goals, when we're measuring this to try to see how can we see how much better is this technique than a typical story and a half or attic retrofit. We wanted to track air leakage reduction as one of our metrics. Moisture management was important. We wanted to increase the R value as effectively as possible, and we wanted to minimize any thermal bridging that would occur across roof rafters. Appropriate ventilation, obviously you tighten up a house. We want to make sure that we're taking a look at the indoor air quality, that we have appropriate ventilation rates with either mechanical ventilation or air exchangers. And we want to also make sure that we're dealing with combustion safety and we're not leaving the house in a situation where we could be backdrafting an atmospheric appliance. So let's take a look here at case 1. This house is a story and a half that, and my presentation is really picture heavy, so I'm going to just plow through these pictures as quickly as I can. But this is a story and a half that had been finished on the upper level and had really severe ice dams. And obviously there's a brick facade here on the outside. And so the homeowner had no choice. They'd spent enough money up in the upper area to, they had no choice but to go with some sort of exterior system. So this is a cross-section that would sort of give you an overview of what this overcoat looks like. So this would be what the actual framing looks like if you were to peel it back. And what we do is we go ahead and we chop off this eave so that we can expose that heel condition and the top of that interior wall. And then at that point we can fill that with closed cell spray foam. And then you'll see here that we're able to infill that with plywood and then wrap a waterproof membrane up and over that corner and tying that membrane into the existing WRV that's behind that brick. The next phase here is we add another layer of 2 inches of polyiso rigid insulation, and then we're going to build out a new soffit and freeze with a new intake for ventilation. This membrane then continues all the way up over the existing roof deck, and that completes our air and vapor control. And then we're going to add 2 layers, 3 inches thick each, so a total of 6 inches of polyiso foam. And then on top of that is a 2x4 that's laid flat, 16 inches on center, spaced with a screw that goes from the 2x4 all the way down through into the existing framing. And then a traditional roofing system on over the top of that. All right, so let's take a look at that. The first thing is you got to identify areas that are going to be affected by elevating the deck of the roof 7 inches. So for instance, if you can see here, the corner of this window is going to be affected when this roof deck moves up 7 inches. We're going to encroach in there and probably have a drainage problem. This was a flat roof section that was attached. Obviously, we raise this roof up or the roof next to it. We get concerned with we got to move this condensing unit and the elevation here underneath the sill of that window. We've got a pan, a copper pan here behind the roof that we're going to have to deal, or behind the chimney that we'll have to deal with. The other thing, anytime we try to solve problems on a roof, and if we go to this level, is we want to make sure we minimize and eliminate as many roof penetrations as possible. So this was a perfect opportunity to get rid of skylights, which are never a great idea on a roof. But skylights, we've got all kinds of venting. These are bath vents. This is an oven vent. And what we did is we rerouted these vents to the gable end over here. We got rid of these existing box vents and moved it to a ridge venting system, and then we eliminated all of the skylights. Excuse me. Next thing is sequencing the tear-off and the dry end. Okay. Planning of this is really, really important, because if we're going to go to the trouble of doing this project to this level, I want to make sure that I can run an air test on the house and verify that my air barrier is doing what I intend it to do before I cover it up with insulation and roof. So we want to make sure that we can go in and practice this thing in sequence and execute in a way that allows me to test and verify along the way to make sure we're doing this correctly. First thing that we do is we go into the attic, the upper attic, and we remove all the existing insulation. Okay, and then we run into demo here where we're cutting off all the eaves all the way around the house, exposing that heel condition. Next, we're going to spray foam all those conditions and connections where the top of the wall meets the roof framing or where the gable end meets an interior gable wall. This is that membrane that I talked about. This is a 60 mil peel and stick bituminous base membrane that goes up and over, ties into the existing WRB behind the brick. This is the inside of the attic where we spray foamed with a closed cell 2-pound foam the gable end and then sealed all of those connections. This house, the roof, the existing roof sheathing was skip sheathing, and in our areas, if it's more than ½ an inch, we've got to redeck the roof. So that's why that all has a brand new layer of OSB over the top. And then you see this installer is actually rolling on a primer that helps the membrane stick to the surface. And then here we are putting on that membrane, and that goes continuous all the way over the roof. And here you are with the completed dry end. Now this is the important part. We want to sequence it so that the entire roof got dried in like this. This membrane is our air and vapor control layer, so that now I can do an air test. So I want to run a blower door, and I want to do an inspection from the inside to see if I've missed anything, and then repair it. Because obviously now the repair process is really simple and really cheap before I start going up on the roof and putting insulation and roofing on. Next thing here is to run that perimeter polyiso board, which is this board right here, all the way around that exposed heel condition, all the way around the house. And then we start framing out our new lookouts for the soffit assembly here and here. You can see that runs all the way around perimeter. And then we're going to attach this foam board. We're going to connect it to the roof foam using just a 1-part can foam. And then this foam starts to get installed on top and work on our way up the roof. Here you can see this is the original roof deck, and here's the side built up. So you can see the change in architectural elevation that occurred there. Here we are installing the 2x4 sleepers, 16 inches on center. And then obviously we run into a problem when we get to this valley, because if we run sleepers, we cut off communication with just a straight run. So what we did to get airflow from the soffit up into this cavity to ride all the way to the peak works really fine here on these common truss areas, but in the valley we had to segment these, and that allowed air to come in and cross through to each of these, and then actually air could move across the actual valley line as well. We left the original freeze board in place that covered the brick, and then we installed a new freeze board over the top with a gap in between, and this gap served a purpose to help us with venting intake down at the lower end. Between these boards is a venting product called core vent. And here you can see that core vent installed right there. And then just a regular stainless lineal intake vent here for the intake of the venting system. Here's how we handled those windows. We just simply built in a window pocket and then lined it with copper. And then re-roofed it just like you normally would. And there's the house finished. And as you can see, it looks, it actually made the house look a lot better architecturally, beefed up the cornice line a little bit, and you can't really tell that this thing had a lift, a 7-inch lift on it. So final testing on this house. This house had a total air reduction of 491 CFM on the blower door test, or 1 air change. And I'm going to go back to, at the end of this, why or how that is significant, because your first reaction should be that's not a huge reduction for that amount of work, but that was something that we learned on this house and on the next house as to what to expect for an air leakage reduction. So here's case 2. Similar house. This one happened to have brick as well. This one had a little addition off the back. The difference on this one was that the homeowner was going to remodel this entire upper area in conjunction with what we were doing, and part of their plan was to figure out how to insulate it, and they felt like the exterior insulation system was going to be the best. So here we've got existing insulation that we had to remove. We got in, demoed the house, tore up all the roofing, exposed the original roof deck. Here you can see that skip sheathing that's in place there. This is on the newer edition. And then we rolled our primer over everything, ran our primer down and tied into this 30-pound felt that's behind the brick. The membrane went over the entire roof, over the edges, tied into the WRB that was existing there. Okay, and then here we are with the complete membrane system. Same thing, run our air test, check for leaks, repair them now as they're simple, and then start building our cornice. Same thing on the gable ends, we spray foamed the insides. I'm going to go back to this one because we did this one a little bit different in that we tested the house right after membrane, and then we spray foamed the gable ends, and then tested again to see what kind of reduction we got just from the surface of the roof deck, and then how much reduction we got from the, including the gable end walls up in the attic. We thought that would play into it because that's the main difference that occurred between the first case study and the second case study. Same system here. We ran the polyiso around the perimeter, built out our soffit, tied in the soffit, or tied in the foam to the heel foam there. Staggered our seams all the way up. Built out a new fascia detail. Tied in our sleepers, and then redecked, and then re-roofed. And here you can see this is our venting detail at the top, where we just cap this with a ridge vent, and that's our exhaust technique here at the top. We had to reflash the chimney with copper. We had to build out another window pan here as well for the same condition. And then the homeowner, in addition to this, was also wanting to install a new front entry roof system, so we overframed that right on top of the overlay. So that's how that ties in. And then here's the house finished. This house the previous house was painted wood. This house is a aluminum coil stock wrap, so these are all custom bent pieces of aluminum. Now this house had a much significant reduction, much more significant than the first. This house was about a 56% reduction, or 1,636 CFM, almost 4 air changes on this. So what does that suggest about the effectiveness of this system? The thermal imaging done in conjunction with the blower test suggests that the methodology, the effective air sealing that was done was very effective. So the key to that, though, is to know that the surface you're changing, the surface you're applying the membrane to, is only going to show as much of an improvement as of how leaky the surface was before. So in other words, if I look at the house and I say that the house has a cube, has 6 sides to it, and I'm only touching one of the sides, I'm only going to be able to affect the leakage on that one side. So if a house is leaking equally on every single side, I only can reduce it by the most of 1/6 of a reduction. And so that was one of the things we learned here, was that this house had a lot more surface area that we affected that was much leakier when we began with than the first case study. That first case study had a finished upper area, and a lot of the leakage that we gained, the leakage reduction we gained in case 2 was already taken care of in case 1 prior to us coming in. So that's the reasoning that we discovered as to why the different leakage rates or different reductions were experienced in these 2 houses. So a lot of it has to do with the opportunity that exists to begin with. On both of these, we eliminated ice dam formation, and I put that as a caveat. As a result of heat loss, the occupants reported significant comfort changes and reduction in utility bills. And comparative effectiveness for air leakage, this is that statement, is not readily available without knowing the percentage of leakage that exists from the treated surface area. And if we assume equal leakage per square foot of the surface area, then we can calculate that by just simply looking at the square footage of the area treated. Knowing what is a candidate for an overlay is houses that already have finished attic spaces, houses that have heat loss performance issues. It really helps if the house already needs a new roof, so you can absorb that cost into your project. Also, if the house happens to need eave or cornice work, painting, soffits, gutters, anything like that. Most importantly, the client's got to be able to afford it. Obviously, this application is a lot more expensive than a typical application, but to be able to see how much better does this get us was the point of this project. And we've since then have been able to complete a number of these, decreasing the cost every single time as we go. So with that, I'll hand it back to the organizer. Thanks for your time.
Thank you, Steve. Anastasia.
Okay, hi. So my name is Anastasia Herc, and I at Ibicus. And I'm going to be talking today a little bit about the deep energy retrofit project that we did with NYSERDA. Green Homes America out of Syracuse was our contractor for this project. These are some of the project partners that we worked with, some of the manufacturers, the contractors, engineers of NYSERDA. So the goals for this project included evaluating a couple of different DER strategies, and 4 of those were going to be spray foam on the exterior walls, 4 of them were going to be rigid foam, and then the last was going to be a home performance with Energy Star house that we were going to compare the two to. Some of the other goals were to have the 50% peak load and annual heating load reduction, and a few other things here. The assumptions that we were making when we were looking into what kind of homeowners or what kind of houses we were going to work with on this project, we were thinking about homeowners that were already going to be doing some of their own work or possibly needed new siding or new windows, and that could in turn lead to other upgrades such as HVAC, insulation, all other things. So when we first started talking about this, we were discussing if we should remove the existing siding on these houses or keep it. We ended up deciding that to keep the existing siding would be better so that we're not disturbing any possible lead paint that we might take several $1,000s to fix, and then you'd also get that re-sided look. Then we also were talking about using the use of spray foam, and we just decided to go with that for better ear sealing, less tape than rigid foam, etc. So when we first decided to get all of the manufacturers and engineers and everybody together, we had a little bit of a brainstorming session to talk about how we could do this project. So our strategic planning session included just thinking about different ideas on how we were going to hang the system off of the wall with the existing siding. So we came up with this detail where we are showing adding on the ledger boards over top of the existing siding with the spray foam, having some clips off of those ledger boards, and then hanging 2x4s off of that. So here was an initial concept that we started to design in SketchUp for this. This would be the existing siding on the outside of the house with our system on top, and then the spray foam on top of that. So here is a view that shows all of the components for this system and how it would go up, everything that we would need to hang this system on the outside of the building, using the closed cell spray foam to insulate the wall after the framing is put up. And then we were assuming that the windows could be installed as the framing is being put up as well. Once we got all of the details together, we put some SketchUp models together and built those at the Green Home facility in Syracuse, so we could try to come up with issues before we were actually in the field. So here's one of them that we did with a door and a light to try to get around the electrical issues that might happen here. Anything that might happen at the two-story room band joist area. And here's another one that we did. This one was sort of trying to build out with the windows as well as the interior corner. And again, another light and some electrical details. Here shows a detail of the mock-up that we started to use the spray foam to see if it would go behind the 2x4s enough to fill that area. So here is our first test house that we did. This is a simple ranch-style home built in the 70s. It's about 2,000 square foot. Here's a picture that shows the covering the existing siding with the 2x4 system to prepare for the spray foam. This shows the front of the house where we have the framing system coming up on the left-hand side there. And then we also had a bay window at this house, which we didn't account for before, so we were trying to figure out how the wall system was going to come up and around that bay window there. Then here is a picture of the first installation of the spray foam, where we're using the tent to prevent spray from escaping the area. And in this particular one, the contractor was spraying sort of side to side as an initial idea. And this was one of our lessons learned that we talked about, where this sort of side to side spray actually caused some of the 2x4s to bow out a little bit. So we were talking about either adding more of these clips in between in the middle of the wall, or just trying a picture frame method, which is to fill the outside area of the 2x4 first and then coming in to fill the rest, which ended up working on some of the later houses that we did. This is another picture of where the new wall and the exterior system meets the existing and intersects at the roof. And here is a picture that shows the entire wall being sprayed out. When we first started talking about this, we were talking about possibly having a hardy board as the siding. This particular homeowner wanted to have vinyl, so we had to install this T-ply over the spray foam and then install the vinyl siding afterwards. So here's a view of the final house and what it looked like after we were done. After the whole project took about 5 weeks from start to finish, which included all of the exterior insulation, DER strategy, along with a little bit of HVAC install and basement and attic insulation. So here are some of the air sealing improvements. We went ahead and did blower door tests at different parts of the project. After adding a few things, we did blower door tests at each time, and we did get about a 50% reduction from the start here. We're showing the peak load reductions here. In the end, it was the reduction was less than 50%, which was the original goal of the project. This is some of the estimated and actual costs that we had for all of the work done on the wall. So the actual costs are here at the end. If you remember at the beginning, we had a $10 per shell square foot goal. If you are planning on installing siding anyways, it would come down to about a little bit over $10 a square foot without the siding. So that's why we were looking for people that had already planned on getting siding installed. So here are some of the lessons learned. Again, the installation of some of the ledger boards over the existing siding were difficult sometimes because of the existing siding was maybe not a smooth surface, or some parts were missing or falling off. The brackets in the spray foam were bowing, like I was talking about earlier, with the spray foam installed, so we fixed that situation. Permitting was sometimes an issue because this deep energy retrofit was new and confusing to some of the people that were approving the install. The order of installing the new windows versus the wall were a little bit different than what we had originally thought. The contractors ended up installing it differently, which worked better for timing and for their order of operations. So if we decided to do this again, we came up with a better step-by-step guide, which I'm going to walk through now. So our first step was to assess the existing condition of the wall. The second step was to remove the existing window trim and then fasten the ledger boards through the existing exterior cladding and sheathing. Step 3 here is attaching the metal L-clips on the top and the bottom of the ledger board, one on either side of where the new vertical 2x4 would be attached. And then also in this step, we're removing the existing window and installing new framing for the new window. Step 4 is installing the vertical 2x4s. These are spaces needed based on structural calculations and siding manufacturer requirements, depending on what siding you're using. Step 5 is installing 2 horizontal framing members on the top and bottom of the rough opening for the new window. And step 6 is installing the sill pan. Step 7 is installing the flexible flashing on the rough opening at least 6 inches up the side of the jamb. Step 8 is installing the caulk on the face of the rough opening at the jambs in the head. We're not caulking the sill here. And step 9, installing the new window. Step 10 is installing the jamb flashing. Step 11 is installing the head flashing from the face of the existing wall to lap over the head of the new window. Also, we're taping the flashing at the head using straight flashing tape lapped over the horizontal part of the head framing. Then here in step 12 is installing the vertical framing members above and below the new window and installing the insect screen to the bottom of the new wall. We're also air sealing the window from the interior using non-expanding foam sealant and installing internal jam extensions to prevent exterior spray from getting into the house. Step 13 is beginning the spray foam like with the picture frame method like I talked about before, spraying around the edges of the vertical 2x4s first and then allowing the spray foam to extend under the 2x4s, being held off by the existing wall by clips. Step 14 is spraying the insulation within cavities of the new wall, and then the foam is your new drainage plane here. So we've just put a note on that some siding profiles may require the thin profile structural sheathing that we showed in the example project. And then step 15 is installing the new cladding and installing the new window trim. So that is it for my presentation. Here's my information if you would like to get a hold of me. And then, like they said, our PDFs are online if you want more of that.
Great. Thank you, Anastasia. This is Mike Gessler at NREL. I will be moderating the Q&A session. We've had a number of questions come in. I'm going to do my best to make sure we get to all of them. The first one I'd like each presenter to respond to. We've had a number of questions come in about applicability of these systems in other climate zones, all of these kind of focused on cold climate testing. So Tom, maybe we can start with you and just comment on the applicability of the excavationless approach to other climate zones.
For the exterior insulation of foundations, building science-wise, any foundation in any climate can benefit from exterior insulation. So yeah, barring any other environmental issues preventing exterior insulation, it can work in all climate zones.
Thank you. Tom, or Steve, rather?
Yeah, I mean, pretty much the same thing for us. We find that the exterior insulation retrofit works in all climate zones. Now, obviously, you're not going to be running into ice dams in other climate zones, and you know, like in the same way you would in the northern climate zones. But from a cooling load perspective, I think there's a lot of opportunity to reduce energy use just by moving the insulation to the outside.
And Anastasia?
I agree. I think it's the same. All of our houses that we did test on were in the Syracuse area, but I think this would work anywhere.
Great. Tom, a couple of questions for you. I'm just starting at the top here. There are a couple people asking how long did it take to do that excavationless approach? And then is there a wait time between, you know, once you dig the trench, do you need to let it dry for a couple days before you can pour the foam?
Very good questions. Yeah, it took 2 days. We actually two and a half days. We were hoping to do it in 2, but remember this was our training session where we designed the process. So we sat down and asked each contractor if everything was going smooth. What we know now, could it be easily done? The digging in 1 day and then the insulation in another day, and the answer was yes. And that all depends on some variables in the field, but there should be no reason why an excavator can't be there and leave and complete it in one day. Same with the foaming. And to the, can you start? Is there a cure time to wait before you can apply? Actually, no. We were going to have the foamers follow right behind the excavators, you know, one wall behind, and we just didn't. We had too many other things to deal with. But conceivably, you could do that. In other words, you can be foaming as soon as the hole is dug.
Okay. Another one for you. There were some questions about concerns about water tables with this approach, and then also other waterproofing system needs. I mean, I think the foam serves as the waterproofing layer on the foundation, but what if someone wanted to do something different?
Well, with this excavation method, you can do anything. It's only a matter of money. So if you want to put exterior drain tile in fact, our excavator, the guy who owns that big truck, wants to do that in his own house. We've devised a method of doing it. We haven't done it yet, but it's not something that's out of the ordinary. Water table, other active water issues. There should be an assessment done. This isn't a waterproofing method for every house, but yet for every house there is a method. What we're trying to do here in the first part of our learning experience is develop what would be a good moisture mitigation and thermal, so the hydrothermal improvement from the top of rim down. In fact, in some cases you don't even have to go all the way to the bottom, because at about below frost you start to lose benefit of cost, the dollar spent per square foot of work done in terms of energy saving. So I think it's so versatile that there isn't anything you couldn't solve. In fact, I think Steve at Cocoon is looking at waterproofing methods for homes on lake shore areas.
Okay. Steve, a question for you on the overcoat relative to the roof wall water control transition point. What if the existing wall does not include an existing WRB?
You probably have other issues. I guess would be the simple answer. You know, I think at the end of the day, if you get into a siding or a cladding system where there is no WRB, I don't think you're going to necessarily cause any more issues than you would already have without touching the roof. Short of, you know, if water was making it into the attic prior and the attic was somehow absorbing that problem, and now you're pushing it down to the walls, it might show up in a different location. But like I said, that's just moving a big issue from one area to the next.
Mm-hmm. What about structural concerns with existing roofs, adding additional sheathing weight, 2x4 strapping, and then the foam? Yeah.
So we had a lot of questions about that. When we did our first one, happened to be in a town called St. Louis Park here, which is really infamous for its inspectors being really involved. But they required structural engineering on this. And what we actually learned through our calculation, you know, kind of my assumption, but we had an engineer prove it, is that by increasing the depth of the roof plane, by basically bonding it all together, you create a much deeper beam, right? So you actually increase the strength of the roof structure, and in some cases we saw that deflection was coming out of the 2x4 that was in there to begin with. So we in effect are stiffening the roof rafters by adding multiple layers, and then bonding it all together with our fastening system actually makes it like a big monoplane system.
Mm-hmm. Let's see here. I have a question about testing over longer periods of time on performance and any potential impacts on indoor air quality. Did these systems necessitate, you know, Steve, for example, the data you showed, did you get to a point where you had to add mechanical ventilation with this type of approach?
Yeah, this house specifically, case one, we ended up backdrafting the water heater, so we ended up replacing that with a sealed combustion unit as a result of the air tightening. And then additionally, when they did that half-story remodel, they installed a new mechanical system up there in that upper area to handle all the heating and cooling. And we believe that that system was already slightly oversized to begin with, but the work that we did definitely pushed it into an oversized scenario. So we got called back the following summer because of a smell, and we determined that it was a humidity issue as a result of short cycling on the air conditioning. And so we weren't pulling moisture out of the airstream because we weren't getting a long enough runtime on the air conditioner. So we had to downsize the air conditioning system to solve that problem as well. Mm-hmm. From a ventilation perspective, they happened to have bath fans in the upper level that were of the type that you can run continuously in the background, and then when you turn them on, they can ramp up. And so we were able to actually just adjust the background low rate ventilation to make up for the additional ventilation that we needed.
Okay. It's a question for probably Tom and maybe Anastasia. Are there termite concerns? I mean, particularly with the pour-in foam, but also with the exterior foam approach. I don't recall if there was a termite detail at the base there. Tom, why don't you go first?
Okay, what's a termite again? I'm just kidding. We don't have those up here. So I've heard and read that it would be a problem. They like to eat foam and stuff, and I've also would want to look more into that. I think there's some ways to mitigate that with, I don't know, chemicals inserted into the foam or wrappings or something, but that's an area I can't answer very confidently.
Okay.
Yeah, as for ours, we did put the bug screen on the bottom of our wall system, but we didn't look into that much more. Duncan, is there anything else that you wanted to add to that?
Well, it just the exterior foam is at least 8 or 10 inches off the ground, and that gives you sort of the inspection strip that you would need for the termites. So okay. We didn't really give them a pathway from the ground to the foam in that application.
Tom, another question for you. Any idea how this approach might work in parts of the country that have, say, real sandy soil or more loose soil? And I know you had a couple of collapses, but are there limitations in terms of the characteristics of the soil?
Yeah, if there was, you know, sand fill all the way around, you know, it's going to cave in. It's going to be loose. There are epoxy injection systems that you can use, little pricey, but can help in that situations. Are you talking about slab on grade, or would you have actual basements in sandy areas as well that I'm not familiar with? But that would be a problem, and I think we just haven't spent any time looking into it. There's got to be ways to deal with it to shore up the wall itself. Of course, if it freezes, you can do it in the winter and you don't have a problem.
Question on the foam you used. What's the R value per inch? So what's the total R value of that subgrade assembly? And then is this BASF foam commercially available?
Yeah, the foam that BASF formulated is R5 per inch standard, similar to what you see in the wall spraying, and it was upgraded with some formula mixture that would keep it much more resistant to moisture absorption. What was the other question about? Oh, is it available? Right now, it's available if you call the rep we work with, and it can be shipped because they're such a big company to any regional area. So it's sort of available. I mean, they're willing to begin producing this as the demand grows. It was based on a formula that that was similar to mud jacking, and so it's not too hard to throw together in the lab or in the production area.
And can you say again what specifically the name of this dirt vacuum system is? So if we had a question come in from Vermont, and if he's looking for a contractor who does he look for?
Hydrovac excavation. Just Google that and put your name in, or the town name in, and it'll come up. Hydrovac excavation.
So have a couple of questions here for you, Tom, again, on if someone wanted to do this but just use rigid sheets, say they have a poured concrete foundation, just wanted to use rigid sheets, is there a way you'd recommend doing that, and what risks might be involved?
Well, if you use rigid sheets, first of all, it won't work at all or hardly very well against a rough surface like you saw in my presentation. If it's a smooth, like poured concrete or block, you still have a problem you need some sort of a water barrier that's adhered to the concrete or the block, and that is done with this liquid foam. That's why we use it against the wall. So if you can reach down there and put a peel and stick, or in some cases we've looked at liquid applied installers that can rig up a special nozzle that will reach down and spray and coat that wall. And actually that is fairly reasonably priced per square foot to do a 60 mil spray on membrane, and then you can easily use 2 or 3 inch XPS against that.
Okay. I have a couple questions for Anastasia and Duncan. The first one being, can you speak to the advantages, disadvantages of using a closed cell versus open cell product? And then I have a question on a structural concern, but I'll let you answer that first.
Duncan, you want to answer the closed cell, open cell?
Yeah, the primary reason for using the closed cell was to have it be act both as an air barrier and as a water-resistant barrier for the exterior of the building. So we had a secondary drainage plane behind the siding. That was the primary reason for using the spray foam, the closed cell foam.
Okay. And there was a question on the clips. Are 2 clips per stud strong enough to support the new wall sheathing and siding, and are there, what limitations might exist there, say you wanted to use a heavier cladding material?
I think that when push came to shove at the end of this, we used the clips initially as a strategy to be able to account for any variation in the depth of the wall, or how far, basically to be able to keep a plumb wall going regardless of where the ledger was. And based on the work we did with the crews and the cost of the clips and things, we determined it's probably more cost effective to take a little bit of time and just shim the ledger boards out so they're consistently off the wall, and just use the simple joist hanger at the bottom as the vertical load bearing member. Would be probably cheaper, easier to do, and more kind of more universally accessible in terms of being able to purchase materials. The clips were a standard clip, but they were more intended for use with light commercial curtain wall assemblies.
Also, we did do some structural calculations in the beginning with those clips, and we did them with the Hardy, because that was the original product that we were going to use.
Can you just comment again as to why T-ply was needed for the vinyl, and would that always be needed?
Well,
we did that. Go ahead,
ahead.
Duncan.
No. The T-ply was basically, if you look at any vinyl manufacturer's installation instructions, they say always install vinyl over a solid surface. And so that was the reason for the T-ply. What will happen with vinyl is if you apply it over an open rain screen, it is impacted by strong winds and will rattle and shake and can self-destruct much more easily than if it's over a single continuous structural sheathing. So we use the T-ply as the lowest cost option there. But check with your vinyl manufacturer, because there may be vinyl products that don't require a structural sheathing behind it.
In terms of alternate approaches for exterior, say you were going to apply a stucco exterior, would you recommend this fur-off spray polyurethane foam approach, or a rigid insulation system if you're going to use stucco?
I would use, if I was going to do stucco, I'd probably use an exterior rigid applied board stock with either a 1-coat or 3-coat stucco, probably a one coat stucco over that, if you're going for a stucco approach.
Okay. I think I have tried to get all these questions here. Does anyone have any additional questions for the presenters? Could type them in real quick. Okay. Well, thanks again, everyone. I think I know I learned a lot. I hope everyone else on the line did as well. We'd like to ask our audience to take a minute to answer a couple quick survey questions on the webinar from today. We have 3 short questions for you to answer. Your feedback is very important to us, and it allows us to know what we're doing well and where we can improve for future presentations. Heather, can you please display the first question? Okay, the poll is open. If everyone could just take a moment to vote. Thank you. Heather, can you please display the next question? And lastly, the third question. Okay, thanks everyone for taking time. Just want to remind everyone our next webinar is scheduled for June 25th at 3 p.m. Eastern. It's titled, Who's Successfully Doing Deep Energy Retrofits? And the webinar will focus on specific VA projects and case studies that highlight real-world examples of deep energy retrofits that are successful both technically and in the market. The webinar will focus on technical strategies, modeled and actual performance results, and real project costs. I want to remind everyone that PDF copies of the presentation from this webinar are available, the link shown. And I'd like to just extend a hearty thank you to all of our expert panelists and to our attendees for attending. It's been great. We had a lot of great questions come in. And I would invite everyone to check the Building America website over the next few weeks to see what other webinars we have scheduled for the rest of the year. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar. Thank you.